So we kind of skipped over valence bond theory. So don't worry about it. We're going to talk about. Well, actually, no, this is from Chem 1. You already did this. These different orbital shapes. We're going to focus on square planar and octahedral. And as I was explaining to my Chem 20 class, Lewis structures, Lewis theory, is the butter knife of molecular bonding theories. It works for so many things, but there's also way more precision things that it's not good for. Valence bond theory is like another one of these. Maybe it's the spoon, if Vesper theory is the fork. I don't know. We've got all these tools that get used together. And we need different tools to explain different things because what we are ultimately trying to do is super simplify really complex things that are happening at the molecular level. And so these simplifications only go so far. The fact that the simplifications work as well as they do is actually kind of crazy and speaks to like there is some order down there at the molecular level. So one of the things that valence bond theories, or the two things really that we're going to talk about that valence bond theories don't explain, are the colors that we see in complex ions and also magnetism. It's not explained by valence bond theory because it comes down to how the electrons distribute themselves in orbitals. So crystal field theory is another simplified theory trying to take something really complex and boil it down to some simple principles that can be applied broadly, but not always specifically, because things are ultimately more complicated. So when we have complex ions, we have, well, they form because of these attractions between the electrons on the ligands and the positive charge of a metal cation. And actually, I think there was a slide that explains how, like, anytime you dissolve any metal, even if water is the only thing around, it's essentially forming a complex ion with water. We usually don't talk about it because the water complex ion doesn't really do anything all that interesting, although we will look at how water as a ligand can change things.
I may have missed it. Definition of a ligand.
Oh, the ligands are all of the things. Do you have a good picture? Yeah, here we go. Anything that's attached, sort of connected around this complex ion. So like in hemoglobin is like a ligand on there's like iron centers. Those iron centers are essentially complexed with the rest of the.
Okay, so it's anything attached to a complex ion.
Yeah. A Lewis, something with lone pairs specifically. Yeah, so the ligands are Lewis bases, which means that they have lone pairs that they can donate. The metal cation centers are the, sorry, my brain cannot, I have to say, it's the chewy nougaty center, like in candy. It's the Tootsie at the center of the Tootsie Pop. They are the Lewis acids in the middle. And it like this extends even further because they're called, the ligands can be either monodentate, bidentate, or polydentate. Like dentate as in teeth, like dentist. So they are even described, and I heard people say this at the conference this last weekend, how the ligands bite into the metal cation. So somebody had, I don't know, candy on the brain when they were describing these things. So the ligands are all of these, Lewis bases with lone pairs that end up sticking to the metal cation because positive charge, negative charge. Crystal field theory explains some of the behaviors that we see of complex ions using unhybridized d orbitals and thinking about how the ligands interact with those hybridized d orbitals. So when you get actually, perfect time to switch to the, switch to this. Should have made these smaller. Let's just move this out of the way. Let's make all of these bigger. Maybe go one at a time. All right, so yeah, let's go one at a time. Oh, I can't see the bottom of that page. That's cool. Who programmed this? Kind of not me, honestly. It's chat. I just asked chat to do stuff. All right, so dz squared, one of our d orbitals, dx or x squared y squared, which is on the x and y axes. You got dxy, which goes on the xy plane, but in between them. YZ, which is in the YZ plane. Nope, come back. All right, so it's like in this plane of YZ. Did I mix one? XZ? Yeah, we missed XZ. XZ is on the XZ plane, but the lobes extend in between the axes. So we've got all of these d orbitals, and when our ligands form, and this kind of goes hand in hand with valence bond theory, when our ligands form these shapes like square planar and octahedral, the ligands will line up with different d orbitals. And those ligands have their little lone pairs. The little lone pairs are attracted to the metal center. When those lone pairs come in, and now I've got electrons that are close to one of these orbitals, it changes the energy of that orbital. It makes it harder for electrons to be in that orbital because they feel essentially this pressure from the ligands on the outside as they get near to those orbitals. And this is really what crystal field theory is using to explain all of this. I've got orbitals where my electrons exist. If ligands come and start to associate with the metal center, they will line up with some of those orbitals. The orbitals that they line up with now are harder to get into because there's a negative charge that's nearby. And so the energy to get into that is now higher. It becomes crowded. It's like a popular bar where you have to pay a cover. Harder to get into. There's a line outside. And that explains some of the behavior of these complex ions. So here, d orbitals, right? If I have just an atom that's by itself, its d orbitals in its ground state, just like the p orbitals, are all at the same energy. That's why they're called degenerate orbitals. They're degenerate because there's not multiple states. There's only sort of one energy level for all of them. But as soon as I introduce a ligand, that ligand gets close, and now they're not equal. And so this is the splitting of crystal field theory, or crystal field splitting. And actually, go back over to this. I'm just gonna reset the page. So these are my ligands on the outside. You can see on the top right there, I've got the field splitting. If I bring my ligands closer, then certain orbitals get higher in energy. The orbitals that get higher in energy are the ones that the ligands are the closest to. And so it's actually going to be the x squared minus y squared, and the dz squared. You can see that, just carry this over here. Right? This is the x squared y squared. It's got all of these ligands that are now close to it on top and close to it on the bottom. And the electrons of those ligands make it harder for electrons to get into that orbital. Yeah, so like the metal center overall is just like a positive charge. And these lone pairs are just lone pairs of electrons, which have a negative charge. And so, especially in a solution, and like I think this ligand ligand that's on there is water right now. Yeah, water. So like any metal cation that you throw in here, waters are going to line up with all of these different spots, or at least that's what crystal field theory says. And when those lone pairs on the water get close, it causes these orbitals to now be not equal in energy. And the closer that they get, the more pressure that they sort of put on those orbitals, the more we see that energy split. Now, for a real ligand, I mean, they'll be like moving in and out, but the proximity of the ligand will depend on the charge of the metal cation and really the size of the ligand. So if a smaller ligand can actually get closer, and a higher charged metal cation will be more attractive to these lone pairs, and so get pulled closer. So the reason we get this splitting pattern with an octahedral is because in the octahedral, my ligands are aligned with the z squared and the x squared minus y squared orbitals. So those get higher in energy. The other ones also are a little bit higher in energy, but because they're still kind of far away from those ligands, their energy increases a lot less. And this has big impacts for how these orbitals fill. Because according to, was it Hund's rule? I thought Hund's rule was, oh no, it's the other one that I don't really talk about in Chem 20. But the rule where the orbitals fill from lowest to highest energy. Right, so electrons will go into lower energy orbitals first. As we fill the 1s first, then 2s, then 2p, because they get higher and higher in energy. Well, if I have ligands around and they change the energy of these orbitals, then my orbitals will fill differently. And it'll also kind of change how we apply Hund's rule. So this rule is the one where we go one electron each first before pairing up, because there's an energy cost for pairing electrons. So all things being equal, if I've got orbitals that are all the same energy level, I'll get one at a time. Because why am I paying the energy cost to pair things up if they can be separate? But when we get ligands involved, now we can think about the energy cost of pairing up might actually be less than the energy cost of going to the higher energy orbital. And to simplify this, because you could do the math and you can calculate the energies, we're not doing that. We kind of split up our ligands into different types of ligands or complexes. So strong field complexes, where the splitting is large. So a big gap between our lower energy orbitals and our higher energy orbitals. And then weak field complexes where the splitting is small. Actually, I'm going to do this a little bit out of order because I want to talk about the ligands first. So how do we know what kind of complex things are going to form? You can essentially just rank everything in terms of really their ability to split the orbitals, which is based on a couple of things. I already mentioned one, the size. So size is a factor, doesn't explain everything here. Electronegativity is the other factor, which it doesn't say on the slide. But as we just look at our weak field ligands, so these are ones that are going to cause less splitting, or a smaller split between our orbitals. You can see as we go to the right, things get larger, especially between my halogen series. Chlorine, fluorine, bromine, and iodine. Iodine's really big. And so when it comes up next to a metal cation, it can't get very close. And so the splitting is less. Bromine can get closer and has a similar electronegativity. Chlorine can get even closer, has a similar electronegativity. And actually, if we go over here, right, we could just kind of look at, even if I just do water, right, iodine would be really far away. As these get closer and are able to get closer, those orbitals split more and more. The other factor is the electronegativity. So actually, let me write this on here. Large ligands can't get close enough. So we get small splitting. The other thing here is electronegativity. And especially if you look at the middle of the series here, you notice a triangle with electronegativity. Which elements of the strong field? Oh, yes. Is it high or low electronegativity that gives me the stronger field ligands? Yeah, and electronegativity, but just using electronegativity, right? Fluorine's the most electronegative, and it's on the weak field side. Oxygen is less electronegative, but it's still more than, well, OH minus is going to be more electronegative than water. And then less electronegative than oxygen is ammonium or nitrogen. And then these get even less electronegative. So electronegativity is reversed. Usually we think of electronegativity, or at least the way I describe electronegativity, is the ability of an atom to pull on and hold on to electrons. So why do you think fluorine is a weaker field ligand than ammonium in terms of electronegativity? Well, it's weaker field, that means it's not actually pushing on those orbitals as much, which means they don't split as much.
Because it wants to take the electrons, not bond with the positive nucleus.
Honestly, that could be part of it. I think the way that I think about it is that the electronegative elements, because they already have those octets. But everything here is octet satisfied. So fluorine usually really wants to get electrons, but once it has those electrons, it chills out. But it's also going to hold on to its electrons very tightly. So when fluorine comes up to, and it's got its lone pairs up to a metal cation, it's already holding onto its electrons really tightly. So it's not going to be putting that much pressure on the d orbitals of the cation.
Because it's harder for the cation to hold on to fluorine's electrons.
Just because fluorine's sort of sphere of influence is smaller. It's got its electrons pulled in, whereas something like oxygen or ammonium, or we go all the way up to cyanide, it's less electronegative. Its electrons are not held onto as tightly, and therefore when it comes close to the metal cation, it pushes more onto that metal cation. Or you could even think about, because they are Lewis bases and they want to donate lone pairs, its electrons are more likely to jump ship and go to the metal cation and interact with that orbital. So we've got these electrons that come up, they're not being held onto very tightly, they're starting to get pulled on by that metal cation. And even with some partial interaction there, that's going to make it harder for other electrons to get into that orbital. Because it's sort of being crowded, it's sort of being squished. Actually, I don't know that this shows that all that well, but I can show you, like, if this is the splitting for water, splitting for cyanide is bigger. But the idea that I think electronegativity is the number one thing. So these guys are putting pressure on this orbital because their lone pair reaches out more. That's what I should have. That's another little ghosty blob that like extends out more for a weaker field purpose. So if something's not holding onto its electrons very tightly, even if you can get close, it is putting more pressure on the d orbitals that it's close to. I think actually this is most apparent for square planar. So if I change the geometry here, and I should make these different colors too. So I got all of my orbitals in here. And if we look at the splitting, right, my dxz and my dyz are the lowest energy. So if I, oh no, that back. All right, just do it this way then. So that kind of makes sense. The pressure that these ligands put on the orbitals is what causes them to split. This is what causes them to be higher in energy. And the fact that like the z squared interacts the least is why it's the lowest on, can I zoom on that? Yeah. Right, so dz squared is the lowest of those three higher energy orbitals. xy is the one that's sort of in line, or it's like in between all of the square planar ligands. So it's going to be higher in energy than z squared. Dx squared minus y squared is pointing at, like directly in line with all of the ligands. And that is a published website, so you can play with that. Well, let's keep this in line with small splitting. So high electronegativity means holds electrons tightly, equals small splitting. Okay, so I said this explains magnetic properties and it also explains the colors, at least for some ligands. The reason that this explains the colors is because as these orbitals split, I change the available electron transitions for that complex. And so the amount of splitting, and I have to get that everywhere. The amount of splitting changes the amount of energy to transition between these orbitals. So a compound that has a small splitting, a weak field, complex ion, when those electrons get excited, the jump that they make up and the jump that they make back down is smaller. And if it's a smaller jump, is it higher or lower energy? Small jump, high energy, low energy.
Jump less energy.
Less energy. High jump, more energy. If we have more energy, we're releasing higher energy light. Then we get different colors depending on that. So, right, black is absorbs all wavelengths, white or clear. Well, actually, white would be reflects all wavelengths. We're talking about absorbing light, right? It's the light that actually is allowed through that complex. So the red solution here is allowing red light through, but not other colors of light. The blue complex is allowing blue light through, but not other colors of light. So really, it's the amount or the frequencies of light that get absorbed rather than the light that gets emitted.
It's like a range of colors.
Color wheel. So glad you asked. I have the answer right here. So you can use the color wheel because it'll absorb whatever, if it absorbs the complementary color, then the color that passes through, or I guess, if it absorbs one color, then the complementary color is what passes through and what we see. So we get measure the absorption for like this purple solution is absorbing strongly in the yellow green. So somewhere, oh no. Let's turn that off. So it's absorbing strongly here in the yellow-green region. And so we get some combination of complementary colors on the other side, is what we see. Now, this one is like more complex. You can use this, you can calculate it. I'm not going to have you calculate it. I'm not even sure like exactly what the value of, like if you can look at the color wheel and you can read the color wheel, then you can tell what if it absorbs in 470 nanometers, for example, what color should you see? So if it absorbs in 470, then the opposite color is purple. I said 470, I meant 570. Thank you. Yeah, 570. Yeah, if it was what, 470 would be something like here, so it would be, no, wait, through the middle, orange. Got to go through the middle. Yeah, so it'd be something like orange red at 470. I think what I would rather you be able to do is describe why that is. You don't have to get into the color science of like how we perceive color or anything, but like if I'm absorbing all of those frequencies of light, it's the complementing colors are the ones that pass through and that we actually see. So different than light reflecting off of something, right? Like on this projector screen, this red section is reflecting red light. If we wanted to make a complex ion that gave us a red solution, we need to absorb the stuff that's not red light and let the red pass through. So we would want to absorb in the green region. And then the other light that passes through would be red. So the colors of our complex ions described because the energy of these photon transitions, or the energy of the photon related to the energy that will be absorbed by the electrons as they transition between different d orbitals. And you can calculate that. You need Planck's constant, you need the speed of light, and you need the wavelength in meters. And that's mostly, see, I even wrote 470 down here. That was, oh, because for this problem, is it 470? No, it's 570.
Yes. The solution turned purple because it was absorbing yellow light.
Yeah. In the aspirin lab, the solution turned purple because it was absorbing yellow light.
Before we mixed the iron chloride with the salicylate, it was yellow because it was absorbing. Or no, it was more orange. It was like yellowish orange because it was absorbing somewhere between the purple and the blue. Okay.
Yeah. So it was absorbing between purple and blue, which is why it looked yellow-orange. Yeah. Yeah, exactly. So we can calculate this. We need that in nanometer, or we need nanometers, but we need meters. So divide by 1 times 10 to the 9 nanometers per meter. Oh, actually, yeah, I will show you this because this is the thing that comes up fairly often, is that if you're calculating something like this, a lot of these calculations are not for a large amount of solution. It's the transition of a single electron or a single photon. It's not Raynold, it's Rayleigh. What was the, I cannot remember the name. There's a calculation that you do in the spectroscopy lab in Chem 1. And you calculate that energy per photon, but you want to know the energy of a mole of photons. So then you have to multiply it by Avogadro's number to get the energy of a mole. So this is going to be 570 divided by 1e to the 9. So it's 5.7 times 10 to the negative 7 meters. And then 6.626 times 10 to the negative 34 meters squared kilograms per second, which is Planck's constant. And that multiplied by 3.0 times 10 to the 8, which is meters per second. So this is 3.487 times 10 to the negative 19. That's joules per photon. For this, we want kilojoules per mole, though. So that's why I got to take this number. It's a tiny number, and that makes sense for a single photon. So multiply this by 6.022 times 10 to the 23. And you get 2.1 times 10 to the 5, and that's still joules per mole of photons. So this will be 210 kilojoules. No, 2000? No, 210. Negative 34. 2.1 or 210 kilojoules per mole. There's a lot of energy. We didn't get quite to the last thing, but I think it explains the most important part. I do want to very, very quickly show you at least how this explains magnetism. So again, this splitting, if I put a higher field ligand, something that's going to put more pressure on d orbitals, I'm going to increase the splitting. My complex ion should absorb higher frequencies of light, shorter wavelengths of light. So you could expect increasing the ligand strength or increasing the metal cation center would cause your absorption to shift towards blue as the splitting gets larger. As the splitting gets smaller, absorption will shift towards red. So magnetic properties, this is where Hund's rule, filling in electrons, like electron configurations, orbital diagrams, comes in. So again, there's a energy cost for pairing electrons. Normally, for just a metal ion by itself, those d orbitals are all the same energy. When I introduce ligands, they change those energies by putting pressure on them. So now it could be easier to pair up than go to the next higher energy level. So the main thing that this does is for certain complexes with high field ligands, my split gets larger. And when I start adding electrons or thinking about where these electrons are going to hang out in these orbitals, they're going to be more likely to be paired because I've got some number of orbitals that are really high in energy and therefore essentially inaccessible. Whereas if I have a small, they didn't do a good job of like showing that these are small and large. They're like large gap means a lot of energy to put an electron into this higher energy orbital. So instead of going by itself, it's easier to pair. With a weaker ligand, then my energy levels are closer together, right? So this distance is smaller. Then when I start filling these in, I'll start going by themselves first because it's easier to go into a new orbital rather than pair up. So the iron with the weak field ligand is paramagnetic, meaning we would expect it to have some magnetism. But the iron with the high field ligand or strong field ligand would be non-magnetic, or at least to be diamagnetic. Having unpaired electrons is what makes things magnetic, at least in like the ferromagnetic sense. It'll be attracted to. So in general, field or complexes with strong field ligands have fewer unpaired electrons. They have fewer unpaired electrons because their orbitals are split more, and it's easier to go paired. Sorry, low spin complexes. Yeah, strong field ligands have fewer unpaired electrons. So strong field, fewer unpaired because the orbitals are split and they pair up first. whereas complexes with weak field ligands are called high spin complexes. Well, yeah, because they'll have the same number of unpaired electrons as the free metal ion. So the difference in energy levels isn't enough that it's worth pairing up, which would be most similar to the uncomplexed ion. And these are really the concepts that I want you to understand, and like understand that it's all based on, really it's all based on, first the page. It's all based on this and how those ligands put pressure on orbitals that causes them to split. So basically, I want you to be able to use this to explain magnetism, colors absorbed, whether or not we have paired or unpaired electrons. All right. I do have Life in the Past Lane, game 115, if you have other questions. Oh, I need to sleep.